All right, so we're going to start off with today's lecture on Hess's law. Hess's law is involving a specific type of chemical reactions where certain chemical reactions that take multiple steps to get to the final end equation that we need to get to. Not all reactions occur in just one step. So now what we're going to do is take a look at that class of reactions that has several steps to it, and we're going to look at how that affects the delta H. Delta H is the enthalpy. Remember, the enthalpy is the heat of reaction. So we have to add the delta H for each step to get the total delta H for the overall system itself. Now, we have two rules for solving it. Sometimes the steps are written in the reverse order, and what is listed as the products you actually need to be reactants, and vice versa. When that occurs, you can take that equation and flip it, write it in the opposite direction, and all you have to do is change the delta H. Okay? If the delta H is written in such a way that it's negative, an exothermic reaction, then when we go ahead and reverse it, now we have an endothermic reaction because the heat has switched from the product side to the reactant side. The second rule we have listed up here on the board is if a step is multiplied by a number, then delta H is multiplied by that number. For example, let's say we had the equation H2 plus O2 gives us H2O. And we had delta H of this equals some number. It doesn't really matter what the number is. To balance this equation, we need a 2 and 2 here. Let's say for the Hess's law to work properly, we actually need a 4 here, a 2 here, and a 4 here. We multiply that entire half reaction by 2, so we get 4, 2, and 4. What we need to do in addition to doing that is we also need to take this delta H value and multiply it by 2 as well. Does that make sense? Any questions there? All right, I'd like to go through two examples of Hess's law for you. One that we apply the first rule, and then the second example we apply both rules. So I'll give you a moment to copy down our first reaction that we have listed here, and then we'll go over it. So first thing we want to do with this equation, now that we have the steps and the overall reaction written down, is we need to make sure that the reactants are on the reactant side of our steps and the products are on the product side of our steps. What I mean by that, our first reactant here is carbon as a solid. So we look down, we look at the very first half reaction, and we see that half reaction contains carbon as a solid as one of its reactants. Yes? Okay, so that means that's in the right place. That's where we want it. Okay, we look at the product that's listed here, carbon dioxide. We look at the first half reaction, no carbon dioxide on the products. The second half reaction, no carbon dioxide. Third half reaction, no carbon dioxide. So we start looking at the reactants, no carbon dioxide in the first step, but we do have carbon dioxide as a reactant in the second step. That's not where it belongs. We want carbon dioxide as a product. So this reaction right now is an endothermic reaction because it's a positive delta H. So what we need to do is flip that reaction. We want to do the opposite of what's shown here. Instead of going from reactants to products, we want to go products to reactants. So I'm going to cross this one out, and I'm going to rewrite it in the reverse direction. Now carbon dioxide gas plus a half O2 produces CO2 as a gas. Okay, all I've done, take the products, make them reactants, reactants, make them products. Flip it. Now, how does that affect the delta H? Instead of an endothermic reaction, now we have an exothermic reaction. The number stays the same. All that changes is this plus sign. That is now a negative. Questions on that? All right, we checked the other reactant. The other reactant was O2. We have no O2 in the first step. We have half an O2 in the second step and half an O2 in the third step. We're going to take these reactions and eventually we're going to add them together, just like we're going to add the delta H's together. Do we have enough oxygen on the reactant side? A half plus a half equals 1, right? Okay, so we need one O2 here. We got half and half, so we are going to end up being okay with the oxygen, yes? All right, so that takes care of the first step, reversing the reactions if necessary. The second rule says if the step is multiplied by a number. Well, we have a coefficient of 1, 1, and 1 here. So all we need to do is check to make sure we have coefficients of 1, 1, and 1 in our steps. We find the carbon here in the first step has a coefficient of 1. Good. We find the oxygen. We already talked about the oxygen. We got a half in the second step, a half in the third step. When we add those together, we're going to have a coefficient of 1 there, yes? Okay. And then finally, carbon dioxide in the second step, both, it has a coefficient of 1. So do we need to multiply by any numbers right now? No, we do not. Good. So now we're ready to add the 3 steps together. You remember redox from way back when, January, December. One of the last steps in redox was to add the half reactions together and cancel like terms. We're going to do the exact same thing here. Add these 3 steps together, make one large reaction, and then cancel things that show up on both sides. And here's what it'll end up looking like. We'll have H2O plus CO plus a half O2 plus H2 plus a half O2 is going to yield carbon monoxide plus hydrogen plus carbon dioxide plus water. Okay? Again, all I did was take these 3 half reactions and add them together. Oh, whoops. Thank you for pointing that out. I am missing my carbon here, so I'm going to draw a little arrow up here and go plus carbon as well. You are correct. I missed that. Let me double check, make sure I got everything else. Water, carbon, carbon monoxide, half of water, hydrogen, half of water. Yeah, I got everything else. Yes? Everybody agree? All right, good. So now we're ready to start canceling out. We cancel terms that are the same on both sides of the reaction. We have water here, and we have water here. Gone. We have carbon monoxide here and carbon monoxide here. We have hydrogen gas here, hydrogen gas here. So we end up with carbon plus a half O2 plus a half O2 yields carbon dioxide. Obviously, we're not going to leave them as halves. We're going to combine it together and just have one oxygen there. Like so. Okay? That is what we were trying to get up at the beginning, yes? Okay, these reactions match. That's a good thing. That tells us we got what we needed. Now we're ready to actually solve the answer, which is to do what? Add these 3 numbers together, yes. Okay, and when we add those 3 numbers together, what do we get? Absolutely. Negative, positive is essential because that tells us endothermic, exothermic. The question was, do we keep the negative? Negative 94.0 kilojoules. Okay, remember when you're adding significant figures together, you add to the least number of decimal places. All 3 of our numbers have 1 decimal place, so our answer is going to also have 1 decimal place. Now, the units here are kilojoules per mole. Okay, negative 94.0 kilojoules per mole. Any questions? One more example of Hess's law before we move on in our notes. I'll give you a moment to copy this down and then we'll go over it. So the first step, again, just like we did with the previous problem, we want to make sure the reactants are on the reactant side, the products on the product side. So we're looking for P4O10. We come down to the second step, and we see P4O10 is listed as a product, not a reactant. So we need to take this reaction and reverse it. So we're now going to have P4O10 as a solid produces P4 as a solid plus 5O2 as a gas. That's going to change the delta H from negative to positive. The second substance, PCl5, don't worry about the coefficient right now. We'll take care of that next. We just want to make sure the substance is on the appropriate side of the equation. So PCl5, not in the first step, not in the second step, but in the third step, and it is on the opposite side of the equation that it needs to be. So we're going to take that one and flip it as well. We now have PCl5 as a gas, gives us PCl3 as a gas, plus Cl2 as a gas. And that delta H will go from being negative to positive. The product, Cl3PO, we find that in the fourth step, and we find it on the appropriate side. It's on the product side where it belongs. So we've taken care of the first step. Now we need to deal with the second step, deal with the coefficients. P4O10 has a coefficient of 1. In the second step, also has a coefficient of 1. That's good. PCl5 in the overall reaction has a coefficient of 6 right here. So we need to go ahead and take the third half reaction and multiply the entire half reaction by 6. Which means we also need to do what to the delta H? Multiply it by 6. So we get a new half reaction of 6 PCl5 here as a gas, yields 6 PCl3 as a gas, plus 6 Cl2 as a gas. So now we're no longer dealing with that anymore either. Okay, we multiply that by 6, and what do we get mathematically? 505.2. And again, these should all be kilojoules per mole. Excuse me. Okay. All right, the last one. The product has a coefficient of 10 in the overall reaction, so we come down to our fourth step, and we have to multiply that step by a coefficient of 10. 10 PCl3 gas plus 5O2 gas is going to yield 10 Cl3PO as a gas. And we'll cross that out there. We take the entire delta H and multiply it by 10, and that gives us negative 285.7 kilojoules per mole. Whoops. No, I just wrote the exact same number again, didn't I? Negative 2857 kilojoules per mole. There we go. Questions so far? So we've covered our 2 steps. Now we should be at the point where we can add these numbers together and add these equations together, get the appropriate overall reaction, and get our final answer for delta H. So let's take a look at our work here. When we add the equations together, we get P4O10 plus 6 PCl5 plus 10 PCl3 plus 5O2. Do I have all of them? 1, 2, 3, 4. Good. Okay. Oh, that's right. I'm missing an entire half reaction there. Thank you. Plus P4 and 6 Cl2s. There we go. Now we got everything. Yes? Correct. Then our products 4 PCl3 plus P4 plus, and then I'm going to wrap around here. 5O2 plus 6 PCl3 plus 6 Cl2 plus 10 Cl3POs. That was a lot of writing. Let's step back and double check everything here. Excellent. Yes, we wrote it down correct. Now we start canceling out. We have, let's see, 5O2s and 5O2s, a P4 and a P4, 6 Cl2s and 6 Cl2s. Okay. Then the last thing we can cancel out, we have a total of 6 PCl3 plus 4 PCl3 on the product side. That gives us 10. And we have 10 on the reactant side. So that cancels both of those out. And we're left with just P4O10 plus 6 PCl5 gives us 10 Cl3POs. Is that the reaction that overall reaction we were hoping for? Yes, it is. So now we come back up here. We want to add these 4 numbers together. And we get what? It doesn't take this long to add up 4 numbers, people. What do we got here? Let's go. Thank you. Negative 610.1 kilojoules per mole. We agree with his math? Good. Do we have an exothermic or an endothermic reaction here? Everybody take a look at your notes from the first day of thermochemistry. Is this an exothermic reaction or endothermic reaction? Delta H. Yes. Okay, when delta H is negative, we have an exothermic reaction. Okay, get that drilled into your head. That is going to be valuable when we start to look at Gibbs free energy here. All right, moving on. Spontaneous processes. I'll give you a moment to copy this down and then we'll go over it. So, next topic we have to discuss is spontaneity. Spontaneous processes occur without an outside intervention, some outside force acting upon the object or system itself. Now, these can be kind of tricky. You really have to sit down and kind of think a little bit about them. We look at the first example there, a ball rolling down a hill. Okay, we're all standing at the top of a hill. Mr. Sutton puts his ball on the top of the hill and lets it go. What does the ball do? Rolls down the hill. Okay, now, was that ball acted on it by an outside influence? Gravity. So does gravity considered an outside influence to make this a non-spontaneous process? What you need to start thinking about is not just the ball. Think about the system in general. Let's say we flip the situation. We reverse the situation. Now the ball is at the bottom of the hill. Okay? If you believe that gravity is an outside influence, then gravity might or might not influence the ball at the bottom of the hill to get back up the hill. Yes? Okay. Is that true? Gravity might or might not influence the ball. Gravity will always influence the ball here. Okay? Regardless of whether the ball is at the top of the hill or the bottom of the hill, gravity is going to be an influence on that ball. Yes? Okay? So, the outside influence comes into when the ball is at the bottom of the hill. What does Mr. Sutton have to do to get the ball back up the hill? I got to pick it up, I got to push it, I got to move it in some form or another, yes? Okay, so that is the outside influence. When the ball is at the bottom of the hill, I've got to put a force or exert an effort on that ball to get it back up to the top of the hill. Whereas when the ball is at the top of the hill, I let go, the ball immediately starts rolling down the hill. Gravity is a constant regardless of which situation you look at, yes? So can we consider gravity to be an outside influence? No, gravity's part of the system. So for that first example, we would actually call this a spontaneous process. Now the second one, heat flows from cool to hot. Is that a spontaneous process, or is that a process that would require an outside force, an outside influence of some sort? Yeah, that one's going to require an outside influence. Okay? Think about the language of it. You've got heat flowing from cool to hot. Is that what heat does spontaneously? Energy does spontaneously? No, energy spontaneously goes from hot to cold, right? Okay? That's a spontaneous process. But going from cool to hot is a non-spontaneous process. That is going to require some kind of outside influence for that to occur. All right, Fe, H2O, and oxygen. I take iron, water, and oxygen, put it in a container in the back corner. We let that sit for a week. What's going to happen? It's going to rust. Is there any outside influence on that? No. So that's going to be spontaneous, yes? Does anyone have any questions so far? All right, this fourth one is a little bit tricky to think about. Okay, I take wood, put it in the back corner with some oxygen. A week later, what do we still have? Wood with oxygen around it, yes? Okay, what do we have to add to this system to get the system started? A candle, a flame, a match, something, yes? Okay? Once we add that activation energy into the system and we get to the top of that activation graph, remember that graph from about a week ago? Okay? At that point, once we've added in that energy, will the reaction continue on its own? Yes. So we consider that energy that we put into that system initially part of the system. Because once that energy is in the system, the reaction will continue spontaneously. I will not have to continue to put energy into the system to keep it going. Does that make sense to everyone? Because that's the trickiest one up here. So we consider this to be a spontaneous process. All right, the last one. CO2, H2O makes wood. We got CO2 and H2O molecules in the atmosphere, in the classroom right now. Are they banging together and little pieces of wood are falling from the sky? No. Okay? It's not that's definitely a non-spontaneous process. Okay, for this process to occur, we need sunlight. Okay, we need some nutrients from soil, correct? Okay, but eventually, using carbon dioxide and water, we can make wood, correct? There are just some outside influences that have to go into that one. Any questions? All right, the next topic we have to talk about. We're going to take spontaneity and entropy, and we're going to combine them together into Gibbs free energy. So we need to talk next about entropy. You remember from our last lecture, or 2 lectures ago, I can't remember which. Entropy is randomness or disorder. Now, for determining the change in entropy, we have these 5 rules that are listed on the board here. And I'll give you a moment to copy those down. So we're determining the change in entropy for each of these rules that we have here. The entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas. That makes a lot of sense to us if we think back to August and September last year. When we were doing our little diagrams, our solid was nice and neat and organized in rows and columns. Our liquid was all jumbled up, okay? And then finally our gas was really, really spread out. Okay, you guys remember those diagrams we did from way back when? The idea is This is the most organized, and this is the most disorganized. And they go progressively more disordered from a solid to a liquid to a gas. Now, what does that mean in terms of chemical equations? Let's say we had water in a liquid state, and we added heat to it. Eventually, that water is going to change from the liquid state to the gas state. Okay? When we look at this reaction going from a liquid to a gas, we are getting more random, more disorganized. Therefore, the delta S for this reaction would be positive. And there could be some number that we could associate with that. I'm not too worried about the numbers right now. It's the idea that entropy either increases or it decreases. The change in entropy. Questions about the first one? All right, moving right along. The second one, products have more molecules, creates an increase in entropy. So let's say we had 4 of some chemical and 3 of some other chemical. We brought them together and made 5 of some chemical and 6 of another. Okay? We can literally add up these molar ratios, just like we did in the gas unit. 7 moles on this side, 11 moles on this side. If we've created more molecules on our products, what have we done to the entropy? Increase the entropy. So again, the delta S here would be positive. Questions? Third one, larger molecules are more disordered. Okay, so let's say we're combining water together with carbon dioxide and we're making some kind of sugar. I don't know, C6H12O6. Okay, I know the equation isn't balanced. That's not the point of this. The point of this is that these 2 molecules on the reactant side are relatively simple molecules. 2 bonds here, 2 bonds here. Then we get to this molecule over here, and whoa, holy cow, do we have a much more complex molecule. Certainly many more bonds than just 2, yes? So again, when we make a larger molecule here, we have now increased the delta S. Questions on that one? All right, last 2. Higher temperatures increase entropy. Let's say we had a sample of N2O at 10 degrees Kelvin, and then we had a sample of H2O at 40 degrees Kelvin. Which one is going to have a greater entropy? The H2O, since it's at a higher temperature. H2O has a higher S entropy. Then the last one, this goes back to Boyle's law from the gas law unit. Remember, Boyle's law was volume and pressure are inversely proportional. So if we have a large volume and a low pressure, the entropy of that system will always be greater than the entropy of a small volume and a high pressure. Questions about those conventions or rules? Now, where does this lead? It leads to these 2 statements down at the bottom of the page here. Delta S is positive. That means we've increased the randomness, the disorder, the entropy, and we have favorable conditions. If delta S is negative, we have decreased the entropy. We've actually made the world, or the system, the system more organized, and that's not favorable conditions. This idea of spontaneity and entropy, along with the enthalpy, the heat of reaction, back to the exothermic, endothermic. We're going to take all 3 of those concepts and put them together into one equation. Gibbs free energy equation, which is represented with a capital G. We relate temperature, enthalpy, and entropy. So we have the change in enthalpy, delta H, minus the temperature. The temperature must be in Kelvin. We need temperature to always be positive for the relationship to work. Then we have delta S, which is entropy, the randomness or disorder that we just discussed. When we take those values, multiply the T and the delta S together, and then subtract those from delta H, we get a value. If that value is negative, you have a spontaneous process, a process that is going to occur without outside intervention. If delta G is positive, then you are going to need some kind of outside influence to get that reaction to work. I'll give you a moment to copy down the summary table there, and then we'll go over it. So the summary table down below, the first one, delta H is negative, exothermic reaction, delta S is positive. So we're releasing heat and our products are more disorganized than our reactants. When those two conditions are met, you will have a spontaneous reaction regardless of the temperature. It does not matter what the temperature of the reaction is, it will be a spontaneous reaction. Now, the second one, when delta H is positive, an endothermic reaction, yet delta S is positive, which means we're increasing the disorganization. So we have endothermic and more disorganized. That will only be spontaneous at a high temperature. You gotta have a temperature in the hundreds and thousands to make that work. Then, when delta H is negative, so we're back to exothermic, but delta S is negative, so now our products are more organized, less randomized than our reactants. That'll only be spontaneous at very low temperatures. And then finally, the last one, we have an endothermic process that ends up being more organized with our products. That's not going to be spontaneous at any temperature. You have to have an outside influence on that one. Questions about Gibbs free energy or the summary? We're done.